Hi, I'm Christie. I am its security. So last week, recall that we present the and its succinct arguments. But in reality, what we want is a SNARG. So we also want the non-interaction. Then the prover only needs to send one proof, and the verifier can verify. So that will be the topic today, the Mikali construction. And basically, looking ahead from Kilian to Mikali, we just need to perform. And recall that the Kilian in the construction, it's actually constructed from PCP, and for Mikali, it will be constructed also from PCP and Maple tree, but it's from state restoration PCP and Merkle tree. So a state restoration PCP captures the Fiat-Shamir transformation. So because in Fiat-Shamir transformation, the prover can simulate the verifier response. So you can actually simulate multiple rounds of prover and the verifier interaction, and it will output one of those best try. In order to capture the restoration PCP is saying that even if the PCP prover can run the verifier for example T, it will still it will not make the verifier accept X is not in the language. So this basically captured the Fiat-Shamir security. So let's look at the definition of state restoration PCP. So we use for state restoration PCP, we use a game to capture the idea that the PCP prover can attack PCP multiple times. So the game will have state restoration prover as will take in the state restoration prover, and it will simulate the verifier randomness using random oracle. It also has the actual sort size. So this sort is basically for the Fiat-Shamir transformation. So basically, in the PCP interaction, the PCP prover can output X and the PCP oracle pi. For the same instance X and the PCP proof pi, it can run verifier for multiple times. We basically want to derive different verifier randomness even for the same instance and pi. So this sort size is basically saying that we basically allowing us to derive different verifier randomness even for the same instance and the PCP proof. But S defines the how many sorts you can try for a same instance and the proof. So the game looks like so the game will takes in the output of state restoration prover for in this loop. So it will repeat step 1 until the state restoration prover decides to stop. So in each iteration, the state restoration prover outputs instance and the PCP proof and starts off with choice. So the game will simulate the verifier challenge by hash the output of the restoration prover. and it will give this simulated verified challenge to the PCP prover. And in the end, after it exits the loop, the stereoisomorphism prover decides to give a final output. So this will be the final, the thing it decides to really send to the verifier. So from now on, it cannot try verifier for another time, and the row will be the final verifier challenge. And we say PCP prover is T move if it executes step 1 for T times. So now we have the definition. We wonder how it relates to the original PCP soundness. So recall that for adaptive PCP soundness, the PCP prover can choose an instance and the oracle of by its own, and we will sample the verifier challenge from the uniformly randomly from all string of size R, and we will check if the length of the instance is smaller than, and if it's not in the language, the probability that verifier still accepts. So the difference here is the gain for stereoisomorphism prover allows the stereoisomorphism prover to try T times for more budgeted T, and the row will be output by the gain because gain is honest instead of sample here. So intuitively, because the stereoisomorphism gain allows the prover to try different verified randomness for T times, it will be like on the factor of T less secure than the PCP soundness. So here we have a +1 because in the end, after T iteration, the stereoisomorphism have one more output in the end. So it's in total has T+1 twice. And we will prove this by constructing the PCP prover given a stereoisomorphism prover. The PCP prover will simulate the gain for the stereoisomorphism prover. But remember, on the high level, the gain allows the stereoisomorphism prover to try T times. But PCP prover can only try once. It will output an X pi, and it's over. The row will be some verified challenge that PCP prover cannot get feedback from. So for out of T+1 trials by the stereoisomorphism prover, it will just choose random one try of those T+1 tries and output the J's run of stereoisomorphism prover. So we denote I to be set of indices such that X pi is equal to the output, equal to the, because so remember that the stereoisomorphism prover can try T times, and I is the set of indices that the i's outputs by the stereoisomorphism prover is the same as the final output. Is the same as the final output by the gain. So as long as the J that PCP prover sample, as long as the J that the PCP prover sample is inside this I, it means that this output X pi is the same as the final output X pi of the gain. So indeed, whenever J is in this set of indices, the X pi output by the game and the PCP prover will be the same. And the row on in the first probability is randomly sampled string from of length R, and this row is the output of R&D, a random function. So it's also a random string. So that means the first probability should be at least the probability the probability that the stereoisomation game wins, because the predicate only depends on X, pi, and rho, and all of them have the same distribution if J is in the set of indices. And notice that this event that J is in I is completely independent of all the other events, because J is really a random integer. So the probability a random integer in a set of size t plus 1 is at least 1 over t plus 1 by the probability of independent events. We can separate this probability into the probability of J in I and the probability of rest of the predicates. So that's how we get to this step. And we can you can just switch this probability into another side of the inequality, and we will get to the final bound to the PCP soundness. So is there any question? Okay, I think we are good. And for the knowledge soundness, it's very similar. So the knowledge soundness is just has one. So instead of X in R, we now have XW not in R, where W is the output of extractor. So if we set the restoration extractor to be the same as the PCP extractor, then the proof will be almost the same. The W is the same because W is the same as long as X and pi are the same, because they're the same algorithm. And these parts are exactly the same as the soundness proof. So whenever J is in I, these two will output the same X and pi. And if we just pull the probability J in I out, we will get this t plus 1 in front of the PCP soundness arrow. So now we have a building block. We can go to the real Mikali transformation. I recall that the Mikali transformation is really first apply the Killian transformation and then apply the Fiat-Shamir transformation. So the Killian transformation, I recall that in the Killian transformation we have prover and verifier they can interact with each other. So they both have a random oracle for the Merkle tree commitment. So in the Killian protocol, the prover first simulate the PCP prover, and then it commits to the PCP oracle pi to get the root. So it sends the commitment to the verifier, and the verifier will send a random challenge. Given this random challenge, the prover can derive the query set and the opening answer correspond and the answer that's pi restricted to the square set, as well as some opening proof for the Q and A, for whether A is a valid opening for Merkle tree roots. And then finally, verifier will output accept or reject. So in Mikali construction, we also, because it's a non-interactive construction, we want the prover to just send one pi, and the verifier will output accept or reject. The FS oracle, we have one extra oracle, FS oracle, for the Fier-Shamir transformation. And the Fier-Shamir transformation will allow the prover to simulate the verifier challenge row. So the first two steps are the same. It will non-interactively construct the pi from the PCP prover and the Merkle tree commitment, but it doesn't send to the verifier. Instead, it will derive the PCP randomness itself. And it also, because it derived the PCP randomness itself, it can simulate the third response itself as well. So it can derive the query set from the simulated randomness, and also derive the opening, Merkle tree opening, and the answer correspond to this query set. So it sends single pi, which basically contains the transcript of all the Killian transform. It's perform hash itself, and then it will check. It will run as in Killian construction to check if verifier PCP verifier accept and if the opening is correct. In high level, really, it just the PCP, the argument prover in Mikali construction is just simulating one. It's just the proof is sent. It's basically the transcript of one Killian construction, and it can internally perform multiple Killian verification, and only sends the best one of its choice. So in terms of efficiency measurement, because it's non-interactive, we don't have the communication complexity. Instead, we only have the argument size, which is the size of the single proof the prover sent to the verifier. And the size is basically the same as the size of the transcript of construction in the Killian construction. The prover complexity and the verifier complexity are almost the same as the Killian. So they are both dominated by the PCP prover complexity and the verifier complexity. In this diagram, we can see more clearly that the FMT random oracle can help the prover to derive the commitment, and the FS random oracle is for the Fier-Shamir transformation, that it can derive the randomness for each root the adversary output commits to, and it just need to output one of the row it tries so far. And for the verifier, it will first use the Fier-Shamir to derive the same randomness, and then use the FMT random oracle to do the Merkle tree checks. So now let's prove the soundness. So last week we already know that the non-adaptive soundness and from non-adaptive soundness to adaptive soundness is very easy. The proof are mostly the same. So here we will only prove the adaptive, we will directly prove the adaptive soundness of Helium protocol. So suppose that we have a Mikali construction with let's see. So here the Mikali construction. So we have it's upper bounded by the T+1 times PCP soundness error and the multi-extractability error of Merkle commitment. So recall that for Killian construction, the argument soundness is upper bounded by epsilon PCP plus a single, like the one extraction error for a single extraction error for the Merkle commitment instead of multi-extraction error. So there are two differences to the Killian case. We have an actual T+1 factor, and we have the multi-extraction error instead of single extraction error. So the T+1 error, so recall that I mentioned that Mikali is basically state restoration PCP plus Merkle commitment. And we already know that state restoration PCP soundness is upper bounded by T+1 PCP soundness. Really, we first have the Mikali soundness to be F plus Merkle tree error. And then by this reduction, we have the T+1 in the final bound when we reduce to PCP soundness. The multi-extractability error is intuitively, it's because we can perform multiple, so the argument prover can try multiple times instead of only try once. So the argument prover is able to query FS oracle with different roots, and it can query multiple times. So for each such root, we can extract PCP pi. So that's why we actually try to extract multiple pies for the move and each pi will be used for the first move and the TS in the state restoration game. So looking ahead, that's how the proof will work. So we will construct PCP proof from each query root to the FS random oracle, and each PCP proof will be submitted to the state restoration game. So each root, so because we extract for multiple times instead of one time, this will give us multi-extractability error instead of a single extraction error. So we can first prove that argument is reduced to restoration soundness, and the multi-extraction error of Merkle tree commitment. We will show that these two distributions, where the first one correspond to the argument, and the second one it will correspond to the state restoration gain, and we will show that the difference between these two distributions are bounded by the multi-extractability error of Merkle tree. So the first distribution, we run the argument prover honestly, and we get a single pi. So we will run a single extraction to get the PCP oracle pi from the root that's in the argument proof. And so the 5 tuples we care about are all the query answer pairs in the FMT oracles, the instance X, and the oracle proof that's extracted from the final output root, and the bit that indicates whether the argument verifier accepts. The second distribution is the state restoration game distribution. It will take in the argument prover and simulate with the state restoration prover game. So it will output instance pi and prover randomness itself. And we care about the same tuple, but the bits here, because there's no argument verifier, the bit is instead the PCP verifier bit, verification bits, and some Merkle tree opening check bits. So this bit is to check whether some Merkle tree opening is valid or not. The PCP state restoration prover is constructed as follows. So it takes in argument prover. So the argument prover has access to random oracle FMT and FS. So the state restoration prover needs to simulate the FMT and FS oracle. So it will simulate the FMT oracle honestly without doing any change. But for each FS oracle, it will extract. So there are two cases. Either the query to FS is something contains a root, or it's some garbage query. So if it's something that contains the root, then we want to extract a PCP proof pi from the root, and then we can submit the PCP pi as a move to the state restoration game, and we can the game output will be the randomness we return to the argument prover. In the case where the query is a garbage that doesn't contain any root, so it won't be useful for the argument prover anyways. We will just simulate with some random function with samples itself, and just return row as the hash of such random function. So in the end, the argument prover will output a pi, and the PCP, the restoration prover, will run the extractor the last time to output the last pi it will submit to the state restoration game. And the BMT here will be the bit that checks whether the argument prover outputs something that can be opened successfully. So it basically the bits for the argument verifier breaks into two parts: the PCP verifier and the Merkle tree opening checks. So in order to prove the two distributions are the same, except some probability, we need to show that the tuple of 4 elements are the same on both have the same distribution. And we also need to prove that the queries to the argument prover are the same. Otherwise, if the query distribution in the two distributions are different, then the argument prover is able to tell that the answer it gets from querying the oracles are different in the two cases, then the argument prover can abort. So they have to be the same query distribution. So we will define some bad event E. So this bad event E is basically the multi extractability error. So notice that if the extractor for each root it extracts some pi, it extracts some good pi, then we are just inside the state restoration game. So as long as the extractor works fine, the two distributions should be the same. So the bad event is saying that the extractor doesn't, extractor fails. So it's either the case that the verifier accepts, but the extracted pi is different from the opening. So it's saying that the pi that's extracted in step 8. So the state restoration, in the end, the state restoration extracts some pi from argument prover's final answer. So if this pi is different from A is the opening. A is basically, so the argument prover has some, internally it can run some PCP prover, and it has some PCP or a proof. So this is saying that the PCP oracle that this argument prover internally has is different from the PCP proof that the state restoration prover extracts. Or the other bad case is where we submit two different Fisher-Shamir queries, root J. So we submit some root J in one iteration, and we submit root J prime in another iteration. The bad event is saying that we submit two different queries such that the query have the same roots, but the extractor extracts two different pi in the two different iterations. And this is bad because this is saying this implies that the argument prover is able to find two different openings for the same commitment. So condition on the bad event doesn't happen, we will argue that the two distributions are the same. So we will argue by saying that the tuples, every term in the tuples are the same. And we argue that the queries that argument prover receives in both distributions are the same. So let's first look at the queries to the FMT oracles. FMT oracles, because we simulate FMT oracle honestly without a state restoration prover simulates the FMT oracles honestly, and it doesn't change anything. They should have the same distribution in both cases. For the queries to FS oracle, there are two cases. Either the query to FS is it's composed of, contains the root, or it's just some garbage query that doesn't have a valid format. If it's a garbage query, then it's easy. We just query the G random oracle G that a state restoration prover samples itself. So we in distribution 1, let's call this D1, and maybe the arc, and this one is D stereoisomation. So in the arc, if X is invalid, it's in the bad format. So basically, it cannot be parsed as instance, root, and tau. Then in the arc, distribution D arc, it will the adversary will receive F dollar and in the second distribution, the DSR, it will receive GX. So because both FS and G are random oracle, these two have the same distribution. So let's look at the other case where X is of good format. It's something that contains the root. In this case, the D-arc will query this tuple of 3 elements, and in this restoration, it will submit a move of X tau sigma, where sigma is the root and tau, and pi is the extraction output from the root and the trace in the MT oracle. We can see that so the move is actually it's simulated by the game SR as an output of R&D random oracle. So if it submits a move, what it really gets is actually a result of R&D random oracle, but with pi and sigma instead of roots and tau. So essentially, we are comparing these two distributions. The first one is the output of X pi and sigma, and the second one is the output of FS with input
audio. I think your AirPods might have died.
Oh, can you hear me now?
Yep. Thanks.
Okay, sorry. Yes, I think I was. Yeah, let me go over this part again. So we are essentially compare the output of R&D random oracle, where with input X, pi, and sigma, and the FS oracle output with input X, root, and tau. So because sigma contains root and tau, what is really different is this input pi. So both are random function. So as long as we can show they have the same distribution, then we should be able to argue that the query to the FS are the same in both cases. Indeed, because we condition not E, it means that the first case, so the first case and the second case won't happen. So now we have event E, or now the bad event is the first event E or event 2. So the negation of this bad event E is the negation of event 1 and the negation of event 2. So the negation of event 2 is saying that for the same root, we can always extract the same pi. Basically, that implies for the roots, we have a 1-to-1 correspondence to the pi. So each root corresponds to a unique pi. That means when we query the same x root tau, we will always get the same query. And because RND and FS are both random oracle, if the input distribution are the same, the output distribution should be both random, uniformly random, and identically distributed. So now we know the oracle queries are the same. So that means the argument prover cannot tell any difference in the DR distribution and the DSR distribution. So it means that the pi it outputs here and the pi it outputs in this step should be the same. Otherwise, it means the argument prover is able to tell whether it's the query answered by the real random oracle or by the simulated random oracle from state restoration prover. So basically, everything in the pi, everything output by the argument prover should have the same distribution. In particular, that includes instance x and pi. And because x and because little pi are the same, if we run extract, if we have the same little pi, we will have the we do the extraction on this root will give us the same pi as in the extraction of this root. So if this little pi is the same, the root will be the same. Then the extraction will give us the same big pi. So this part, x and big pi, should have the same distribution. For the randomness row, the randomness row can be argued in the same way. The first one is the hash of x root and tau. The second one is a move to the state restoration gain. So it's actually is the RND of x pi and sigma, which is the root and tau. By a similar argument as in the query to FS, we know that the row here and the row here have the same distribution. Finally, for the bit B, for the DR distribution, the bit B is the argument verifier output. And for the D state restoration, the bit is the PCP verification bit and the MT Merkle tree opening check bit. So we know by the construction of Mikali, the argument verifier is checking first the PCP verifier, and then and then perform the Merkle tree check. In order to show the distribution of B is the same, we will show that we want to show that B equals B arg is equal to B state restoration. Then we need to show in both directions. So in the first direction, we can assume the B arg is equal to 1. And then we want to show B stereoisomorphism is also 1. B arg is equal to 1. It means that there's a PCP prover accept and the vocal tree check is 1. So because the event E doesn't hold, so in particular, the first condition doesn't hold, then we know that the pi q must be equal to A. Otherwise, this is equal to 0, but we assume it's not equal to 0. So we have pi q equals to A by condition on not E. So if we have pi q equals to A, that means the bit the PCP verifier in stereo restoration distribution is the same, is also 1. Why is that? Because this pi is the same as this pi restricted to Q is the same as the answer. In the other case, we assume that the B arg is 0, and we want to show that the BSR is also 0. So it's 0 either if the first part is 0, where the verifier is rejects, or the second part is 0, where the Merkle tree check fails. So in the second case, we know that because we are composed of the two conditions. If this is 0, then if this is 0, the BMT in the stereo restoration case is also 0. Otherwise, if it's 1, then it must be the case that the PCP verifier is 0. But PCP verifier is 0 by condition on not E. That means the pi q is equal not that means pi q must be equal to A. So that will implies that the bit in stereo restoration distribution is also 0 for the PCP verifier. So that's how we prove the two distributions are the same. Condition not E. So then if they are the same condition not E, then it means that the two distributions are the same, except when E happens. So they're the same. Their probability of that event E close in this statistical distance. What is the probability of E? We can see that these two events are very similar to multi-extractability events. What is the multi-extractability event? So the multi-extractability is, so just to recall, here's the definition. In multi-extractability, the adversary can output multiple roots, and the extractor extracts multiple message, extract the message multiple times from these roots. And in the end, the adversary outputs some query set. In our case, it's a Q and the answer and the opening proof. The multi-extractability is upper bounding the event that for some So in our case, we can view the P argument as the adversary for multi-extraction. So the P argument, whenever it makes OS query, it's submitting a route to the extraction interface. So whenever it submits a OS query, the extractor will extract a pi from the root. Eventually, this P-arg will output a query set, the opening of the final root, and the opening proof. So this is actually the root it finally outputs. And this event, this predicate is saying that in our case, we'll be saying that the last extraction pi, when it restricts to Q, is not equal to A. That's output by the argument prover, or the Merkle tree opening, Merkle tree check fail. And this event it's same as our case 2, the event 2. So this part is event 1. This part is it's implied by event 1. So event 1, recall that it's either VR equals to 1. It's the event that VR equal to 1 and pi Q not equal to A. So VR not equal to 1, VR equal to 1 implies that empty check equals to 1. And the pi Q not equal to A are the same in both cases. So E2 in our construction is saying that they doesn't exist I prime such that the root I and the root I prime query to the OS oracle are the same, but they extract to different pi. So event 2 are exactly the same as the second condition of multi-extractability. So that's why the probability of event E happens is upper bounded by the multi-extractability of Merkle tree commitment. So combining all of these together, we can conclude the proof. So we first have the argument prover, and then we construct the state restoration prover with access to the argument prover, as in this construction. And then we already proved that these two distributions are exactly the same. So are exactly the same except probability of E, which is upper bounded by the multi-extractability error. And the tuples we care about are the row X, pi, and B. And the events, the predicates, both probability, only about those things, the pi, row, bit B. So these together is the B argument. And the row are the same. Row are the same by the plane. So because the distribution of those tuples are the same, the probability must be the same as well. And because ending an actual event will only make your probability smaller, so we can get rid of the last predicate and then we can, and then this is exactly the state restoration PCP soundness error. So indeed, we have that the argument soundness error of Mikali is the state restoration error, soundness error plus the multi-extractability error. And by the previous claim about the reduction between state restoration PCP and the PCP soundness, we have a t+1 factor when we reduce to the PCP soundness. So this should conclude the proof.